A walkthrough for the physics triple paper. It's paper 1, the higher tier. You get 100 marks, you get 1 hour 45 minutes from 2020. Question 1A. Radioactive substances are used in the generation of electricity. State 2 other uses of radioactive substances. Right, they use alpha in smoke alarms. We use gamma for sterilising surgical instruments. And also for sterilising food, killing germs. We can use it for detecting leaks or cracks in pipes. We can also use gamma for treating cancer. I'd probably go for treating cancer and sterilising surgical instruments. Part B. Figure 1 is a diagram of a nuclear reactor used in the generation of electricity. P may be used to shut down the reactor when necessary. Q slows down neutrons to enable a chain reaction to take place. State the name of the two parts labelled P and Q. Well, P, if it shuts down the reactor, that's control rods, which would be boron, just in case you needed to know. We basically drop those down into the reactor. The boron absorbs neutrons, slows and stops the reaction. Q slows down neutrons to be able to enable a chain reaction to take place. That'll be the moderator, which is usually heavy water. H3O instead of H2O. The moderator is sometimes graphite. Question C. Explain how neutrons enable a nuclear chain reaction to take place. So basically, a neutron is fired at a uranium nucleus. That nucleus will split up into 2 smaller nuclei, and you'll also get more neutrons being released, and they would be available for further collisions with more uranium nuclei. A neutron collides with a uranium nucleus, releasing 2 to 3 extra neutrons. Which go on to collide with more uranium nuclei, which just means nucleuses. Haha, it's plural of nucleus. Instead of saying nucleus, you can say atom. But never say split the atom, you must say split the nucleus. So to be honest, I tend to avoid saying hit the atom, otherwise it just might confuse you a little bit later on. Question 2. A student lifts a toy car from a bench and places the toy car at the top of a slope as shown in figure 2. Part A. Describe an energy transfer that occurs when the student lifts the toy car from the bench and places the toy car at the top of the slope. Right, well, where do humans get their energy from? Chemical. So your chemical energy, if you lift it up and it moves, would turn into kinetic energy. Or you could say chemical energy going to gravitational potential energy because you've lifted the car up a height. 1 mark for that and 1 mark for them. You could also say kinetic energy turns into gravitational energy because you're moving the car and then you're moving it up a height. So that would be fine as well. Part B. The student lets the toy car roll down the slope. Describe how the student could find, by experiment, the speed of the toy car at the bottom of the slope. Well, as I say to my students, base your explanation on a calculation. So speed equals distance divided by time. So you need to measure some kind of relevant distance. Now they're wanting it at the bottom of the slope. So you could say measure the distance at the bottom of the slope and the time taken to cover the distance, and then repeat, take an average. You must say take an average as well. You won't get the mark if you just say repeat. So there's your 4 marks there. Question C. The student needs to develop the experiment to determine the loss in potential energy and the gain in kinetic energy as the toy car is rolling down a slope. State the other measurements the students must make. Well, the loss in potential energy will be gravitational potential energy. So what's the formula for that? Gravitational potential energy equals mass times by gravity times by the height. And if you're going to get the kinetic energy, that's a half times by the mass times by the velocity squared. Now we've already got the velocity because we've already just measured the speed from this last question. So basically we need to measure the mass and the vertical height that the car is moving. There's mass there as well, so that just proves we definitely need the mass. Measure the mass, measure the vertical height, 2 marks. Part D. When the toy car rolls down the slope, some energy is transferred to the surroundings as thermal energy. State how the student could calculate the amount of energy transferred to the surroundings. Right, so what you've basically got is the car at the top. When it's at the top, it'll have gravitational potential energy will be its maximum. And the kinetic energy will be 0 because it's not moving. When it's at the bottom, the gravitational potential energy will be 0 because the height is 0 if it's right down here on the bottom. But the kinetic energy will be maximum. So the GPE at the start should equal the kinetic energy at the end if there's no energy lost. But what they have said is that there is going to be some energy lost. So we just need to rearrange the equation to get the energy lost. And that's going to be the gravitational potential energy at the start, take away the kinetic energy at the end. So just say you had 100 joules of gravitational potential energy at the start and you only had 80 joules of kinetic energy at the end. That would be like 100 joules take away 80 joules. That would give you how much you've lost, which would be your 20 joules. So generally, the energy lost is the energy at the start, take away the energy at the end. Question 3, Part A. Which of these is a vector? Now a vector has size and direction. The only one of them that's got size and direction is B, the force. B, Part 1. State the equation that relates acceleration to change in velocity and time taken. A equals V minus U over T, which is basically the change in velocity divided by the time taken for that change. Part 2. A van accelerates from a velocity of 2 meters a second, so that's U, the initial velocity, to a velocity of 20 meters a second, so that's V, the final velocity, in 12 seconds, so that's T for time. Calculate the acceleration of the van. Right, A equals V minus U over T. The final velocity was 20, take away the initial velocity which was 2, and it took 12 seconds for that change to happen, and that comes out as 1.5 meters per second squared. Part C. Figure 3 is a velocity time graph for 15 seconds of a cyclist's journey. Part 1. Calculate the distance the cyclist travels in the 15 seconds. Now, the distance travelled on a velocity time graph is the area under the graph. And they want it for 15 seconds, so that is the full area under the graph. So we basically need to calculate that. Now that's a triangle in this case. Now it's not always a triangle, but here it is. And to get the area of the triangle, you do a half times by the base times by the height. So that's a half times by the base goes from 0 to 15, so that's 15, and the height goes from nothing all the way up to 7, so that's 7, and that equals 52.5 meters. Part 2. Another cyclist starts from rest, so that's 0 meters a second, but his acceleration decreases as time increases. Sketch the velocity time graph for this cyclist. Right, so his acceleration is going to start off big and then it's going to go small. Now basically the slope, the gradient of the slope is the acceleration because the velocity is changing over time. So the gradient of a velocity time graph equals acceleration. So it's going to start off steep and then it's going to go not as steep. So it's going to start off steep like that and then it's going to go not as steep. So as long as you've done a curve that starts off steep and then it's not as steep, so you could have drawn it like that if you'd wanted, that's fine. Anything that slopes off like that. Question 4, Part A. The Sun has a mass of 2 times 10 to the 30 kilograms. A white dwarf has got a mass of 3.4 times 10 to the 29 kilograms. Calculate the value of mass of this white dwarf divided by the mass of the Sun. So you just need to pop the numbers in, it's as simple as that. The white dwarf was 3.4 times 10 to the 29. We just need to divide that by the mass of the Sun, which was 2 times 10 to the 30. And that equals 0.17. And that'll be kilograms divided by kilograms. So those units will cancel out. There'll be no units. Part B. Figure 4 is a diagram giving some information about main sequence stars. Luminosity is a measure of how bright something is. An increase in luminosity means an increase in brightness. That's the luminosity there. So that's bright. And down here is dimmer. Part 1. Estimate the temperature of the Sun. Oh, there's the Sun. Temperature. Now that's a funny scale. So it's actually getting colder as you go from right to left. So if that's 5,000 there, what's that? 6,000, 7,000, 8,000, 9,000. So it's going to be about 6,000-ish. Now they'll accept any value between 5,500 and 7,500. Part 2. State how the brightness of a main sequence star changes with its temperature. Right, let's go back and have a look. So this is colder and this is hotter. And we can see as it gets hotter, the luminosity increases, so it gets brighter. They've talked about brightness rather than luminosity, so I've talked about brightness. And they said changes of temperature, so I was talking about temperature. Use their words. Part 3. State how the brightness of a main sequence star changes with its mass. Right, well that's a higher mass star, and you can see it's bright. That's a lower mass star, and it's dimmer. So the greater the mass, the greater the brightness. Brightness and mass. Part C. Nuclear fusion provides the energy source for stars including the Sun. Describe what happens during nuclear fusion. So I showed you nuclear fission before, which was when large atoms got broke up into smaller ones, or large nuclei gets broken up into smaller nuclei. Fusion is the opposite of fission. Fusion is smaller nuclei coming together to make bigger nuclei, plus energy is released. So you'd actually get 4 marks for that. So you pick any 3 of them. Probably these first 3 would be the best if you weren't adding that one on the end. Part D. A nebula may evolve into a main sequence star such as the Sun. Explain how a nebula may evolve into a main sequence star. So a nebula is basically a cloud of dust and gas. In space. Now gravity pulls it together, and as it does so, friction makes it get hotter and hotter. Now really it's got to get to 10 million degrees Celsius-ish. And then what happens is the atoms are travelling that fast that the nuclei can fuse together, and that's when the nuclear fusion starts, once it's hot enough. Remember, for nuclear fusion to happen, this nucleus and this nucleus need to fuse together. But obviously this nucleus is positive because it's got protons in, and this one's positive because it's got protons in. So you need to get to a massive high temperature so they've got enough energy and they're going fast enough to overcome those repulsion forces. Question 5, Part A. A radio station transmits on 97.4 megahertz. To receive the waves, an aerial needs a length equal to half the wavelength of the radio waves being transmitted. Calculate the length of the aerial needed. The speed of the radio waves is 3 times 10 to the 8. Right, so you've got V equals F times by lambda. Speed equals frequency times by wavelength. Now we need the wavelength, so therefore I pop it in a magic triangle. Frequency times by wavelength will go on the bottom, and velocity will go up on the top shelf. Cover up what you're looking for and what you're left with, so how to work it out. So wavelength is velocity divided by frequency. Now pop the numbers in. So the velocity was 3 times 10 to the 8 meters per second. And the frequency was 97.4 megahertz. Now megahertz is million hertz, so that's times 10 to the 6. And that equals 3.08 meters. Now it says that the aerial needs to be half the wavelength. So if we take that and divide it by 2, that'll give us our answer. So that is 1.54 meters. Part B. To investigate refraction in a rectangular glass block, a student uses the apparatus shown in figure 5. Describe how the student should measure the angle of refraction. Right, they'd have to basically draw around the glass block, then they'd have to draw that normal on, they'd have to put little X's where the light goes in and little X's where the light comes out, then move the glass block out the way, then they'd have to join those X's up, join those X's up, and then join where that goes down to there. Then you need a protractor to measure this angle in between the normal and the refracted ray. You must see the angle between the normal and the refracted ray. Now, to be honest, it's only worth 2 marks, but I don't think you can leave out any of those details. I wouldn't feel comfortable, otherwise you're not given a complete answer, really. Part C. Figure 6 is a simplified diagram to show radio waves from a transmitter, moving upwards, then meeting the boundary between lower and upper layers of the atmosphere. Explain what happens to the radio waves after they meet the boundary between the lower and upper layers as shown in figure 6. Your explanation should refer to changes in direction and speed of the waves. Right, well, let's consider P. So this wave is going up. Now that's the normal, and wave P is moving toward the normal. Now, as I say to my students, F, E, S, T. If the wave gets faster, it moves away from the normal. If the wave gets slower, it moves toward the normal. Now in this case, P, instead of coming straight up and coming over here, it's actually moved toward the normal. So it must have got slower. It refracts toward the normal, so it must have slowed down. And what about Q? Well, Q is basically just reflected off the upper atmosphere, and there will be no change in speed. And we know that because that angle there was the same as that angle there. I equals R. Question 6, Part A. 4 students and their teacher do an experiment to measure the speed of sound in air. The teacher stands at a distance and fires a starting pistol into the air. The students see the flash when the pistol is fired. They measure the time from when they see the flash to when they hear the bang. A student drew a diagram of the arrangement as shown in figure 7. The students obtained a value of 240 meters per second for the speed of sound. The accepted value in a science data book is 343 meters per second. Calculate the difference between the student's value and the accepted value as a percentage of the accepted value. Right, so the percentage difference will be the student's value, take away the accepted value, divided by the accepted value. And then we need it to be multiplied by 100 to get it into a percentage. Pop the numbers in. And that equals minus 30.0. So it's 30% smaller than it should be. That value there is 30% smaller than that one. Now the way you can think about that, just say you go into a shop and there was a coat that was 80 quid that you wanted to buy, and then it said it had 25% off and it was 60 quid. Let's have a look and check and make sure it is actually 25% off. So you do the value that it is now, take away the value that it was, divided by the value that it was, multiplied by 100, and that comes out as minus 25%. So yeah, look, it's had 20 quid knocked off and it was 80. So 20 quid is 1/4 of the original price. So that's 25% knocked off, 1/4 knocked off. I hope that helps you to understand where that equation comes from. Part 2. When the distance was 100 metres, the students measured the following times. Explain why their times vary so much. Right, look at how small those numbers are. The biggest one's half a second. That is going to be very difficult to start the stopwatch and stop the stopwatch accurately, because human reaction time is 1/4 of a second. So these times are comparable with the human reaction time. So that's what's going to make it difficult. And that's why the times vary so much. Human reaction time is about 0.25 seconds. The times being measured are so short that the human reaction time is significant. If I was measuring something and it was 10 seconds, then 0.25 seconds isn't really significant. But because these are so short, 0.25 seconds is significant. Plus, different students will have different reaction times. Part 3. Explain one way the students might improve this experiment. Right, you need to try to increase the amount of time. If we can make these readings bigger, then our reaction time won't be as significant. Now, how do we make these times bigger? We need to make this distance from the teacher to the students bigger. Bigger distance, means it'll take a longer time. And that means our readings of the time will be more accurate. Or use an electronic timer. So there's no error due to human reaction time because a computer is doing the measuring. Use an electronic timer so there's no human error due to reaction time as the computer measures the time instead. Part B. Figure 8 represents a sound wave coming from a loudspeaker and shows the effects on particles of the air at one instant in time. Part 1. Draw and label a distance of one wavelength in figure 8. Right, you can sort of see there's a compression there. And you can sort of see there's another one there. And then there's another one there. And on this side, that's a sort of compression, and that's a compression there. So your wavelength is basically that, from there to there. Part 2. Describe the motion of the particles as the wave travels through the air. Right, well, it's a sound wave, and sound wave is longitudinal. And the vibrations are backwards and forwards. In other words, parallel to the direction of travel. So what I mean by that is that if the wave is travelling out that way, the vibrations, say this little particle here, that'll vibrate a little bit forwards and then a little bit backwards. The sound's coming out that way. We take this little particle here, that little particle would move forwards a little bit and then it would move backwards a little bit. So parallel to the direction of the travel of the energy. That's your standard definition of a longitudinal wave. Question 7. Part A. Which of these describes isotopes of an element? Right. Well, an isotope has got the same atomic number, so it's either that one or that one, and it will have a different number of neutrons, so it's that one. Part B. Figure 9 represents a decay that can happen inside the nucleus of an atom. Proton firing something out to become a neutron. Which decay is represented in figure 9? Right, we're going to do this as an equation, so we're starting with a proton. Now, what do we know about a proton? We know it's got a mass of 1 and a charge of 1. What do we know about a neutron? It's got a mass of 1 and a charge of nothing. That's why they call it a neutron. So we need to have conservation of mass. So that mass coming in was 1. Coming out is these two things added together. So we've already got a mass of 1. So the mass is balanced. What about the charge? Charge of 1. Nothing there. So this particle here must have a mass of nothing and it must have a charge of +1. Now what do we know that's got 0 mass and a charge of +1? That's beta plus. If you want to set it out in a more linear fashion, proton 1 1, it's going to turn into neutron. We know that's 1 0 plus this little mystery thing. So we're not sure what the mass is or the charge, but we do know that mass of 1 went in. So this mass plus this mass has to equal 1. So that must be nothing. And a charge of 1 went in. That's a charge of nothing. So this must be a charge of 1. So that is our beta positive, no mass, charge of 1. Per proton kicks out a per positron. Question C. The half-life of cobalt-60 is 5 years. A school cobalt source had an activity of 38.5 kilobecquerels in the year 2000. Estimate the activity of this source in the year 2020. So that's basically 20 years later. And they've said that the half-life is 5 years. So 20 years is basically going to be 4 half-lives. And we know that a half-life is the time that it takes for the activity to half. So it's basically going to half, then it's going to half again, then it's going to half again, then it's going to half again. So it's going to half 4 times. Now you could either just do 38.5, half it, half it, half it, half it, or you can say half of a half is a quarter, half of a quarter is an eighth, and half of an eighth is a 16th. So you could just take that activity and multiply it by a 16th, whichever way you prefer. And that equals 2.41 kilobecquerels. And they wanted the answer in kilobecquerels, so there's no need to convert anything. So you get 1 mark for identifying there was 4 half-lives and 1 mark for identifying that that's a 16th. If you didn't just get all 3 marks for the answer. You don't need to show you're working out, but it's always good to do so. In case you make a little mistake somewhere, at least you'll get partial marks. Question D. Explain what can happen to the body if a person has a prolonged exposure to gamma rays. Right, always give the same answer whether it's worth 1 or 2. You say it damages cells and causes cancer. That's the easiest way of getting your 2 marks. Question E. A GM tube, Geiger Muller tube, is connected to a counter. A teacher places the GM tube near to a radioactive source. A student starts the counter and clock at the same time and writes down the readings shown on the counter every 15 seconds. The student plots the readings with a line of best fit, as shown in figure 10. The count readings up the side, the time along the bottom. Calculate the average count rate in counts per second from the graph. Show you're working on the graph. Right, if we do counts per second, well, that's the counts and that's seconds. So we need to do the y-axis divided by the x-axis. We basically just need to work out the gradient, and that'll be working out the counts per second. Right, if we just assume that that point there is on 0, 0, we can just literally pick any point on the graph. That seems convenient. Right, what about that point, for example? So that's from 1400 to 1600, and there's 1, 2, 3, 4, 5. So it goes up 200, and there's 5 little squares. So each square is 40, and that's 2 squares. So that's 1480. And we'll divide that by the corresponding x-axis value, which was 100. And that's going to come out as 14.8 counts per second. Now you can pick any values you want. I could have picked this value here. That would have been 800 and divided by, if that's 50 and that's 60, then that's 56, and that equals 14.3. So it's not too far away. they will accept values anywhere between 12 to 16. Part 2. The student says that the experiment must have been done carelessly because the data seemed quite scattered away from the best fit line. The teacher claims such results should be expected in radioactivity experiments. Justify the teacher's claim. Right, radioactive decay is random. So the count rate won't be constant. And that's why the data seems to be scattered. There's variations with each reading. Question 8. Part A. A kettle is used to heat water. Figure 11 shows a graph of temperature against time for the water in the kettle. Calculate the rate of increase in temperature at a time of 150 seconds by drawing a tangent to the curve in figure 11 at a time of 150 seconds. Right, go to the time of 150 seconds and go up to the graph. Now we need to draw a line that is straight and that hits the graph at 150 seconds. So if we do a line like that and then just adjust it, and this line should trace what the curve was actually doing at that point. You see, if I was to draw a tangent to the curve there, what is the line doing at that point? Well, it's sort of coming up there like that. So you can see the gradient here is ever so slightly different to the gradient there. So that's why we draw the tangent, to see exactly what's happening at that particular point. Now all we need to do is to get the gradient of that tangent, and that'll give us the rate of increase in temperature. So it'll tell us how much the temperature is changing by, so that's the change in the y-axis, over a certain amount of time. That's the x-axis. So we want y divided by x, change in temperature over time. Now because it's a straight line, you can just basically pick any two convenient points on that line. Right, well that looks pretty convenient because that's exactly 70, 50, 60, 70, 80, and that's exactly 90. And I'm going to pick that point there because that is exactly 100. And this isn't perfect, but it's alright. 150, 160, 170, 174, I would say. Right, so the y-axis has changed from 70 to 100, so that's 30. And the x-axis has changed from 90 to 174. So that's 84. So if we pop the numbers in, the y-axis changed by 30 divided by 84, and that comes out as 0.357. In other words, 0.36. And the answers they would accept is 0.33 plus or minus 0.07, which means any answer between 0.26, So take 0.07 away from 0.33 up to 0.40. So that's 0.33 plus 0.07. We've got 0.36, which is spot on. Question B. The kettle has an efficiency of 91% in supplying energy to the water. The thermal energy of the water increases by 3.3 times 10 to the 5 joules in 200 seconds. So that's basically the useful energy transferred by the device. Calculate the total amount of energy supplied to the kettle in the 200 seconds. So 200 seconds, 200 seconds. Right? Now this equation isn't percentage efficiency. So let's just turn the percentage efficiency back into a normal efficiency. And you do that by dividing by 100%. So 91 divided by 100% will give us 0.91. So that's the efficiency as a decimal. Now we're after the total energy supplied. So we're going to do a magic triangle. Right, what's on the top shelf here? We've got the useful energy. And then that means we've got efficiency times by total energy. Cover up what you're looking for. We're looking for total energy. What you're left with? Useful energy divided by efficiency. Remember to use the 0.91 for the efficiency, and that equals 362637.3626. In other words, 3.63 times 10 to the 5. Question C. A 6 marker. The global demand for electricity is increasing. There is a debate about whether nuclear power generation should or should not contribute to meeting this increase in demand. Discuss the arguments for and against using nuclear power to meet the increasing global demand for electricity. Right, so we'll put the advantages down here and we'll put the disadvantages over here. Right, well, an advantage of nuclear is that coal, oil and gas, fossil fuels, are running out, so we could use nuclear instead, or as well as. Now, unlike fossil fuels, nuclear doesn't emit CO2. Which causes global warming. And you get a large power output, so it's a concentrated source of energy. Now, it can actually last a long time as well once you've built the power station. Right, disadvantages. It is expensive to set up a nuclear power station. And decommission it. Which basically means to rip it down and to make everything safe again. Because you're going to have nuclear radioactive waste that you're going to have to dispose of safely, and that's expensive. So you've got your nuclear waste you need to get rid of. Nuclear waste needs disposing of safely. There is a risk of a nuclear explosion or some kind of nuclear disaster. And the nuclear waste could contaminate the ground. if you have a leak. 1, 2, 3, 4, 5, 6, 7, 8. You'll easily get your 6 marks for that. Question 9, Part A. Figure 12 is a diagram showing a rocket that is sent into space to try and change the path of a small asteroid. Part 1. The rocket has a mass of 5.5 times 10 to the 5 kilograms and is travelling to the right at 14 kilometers per second. Which of these is a correct calculation of the momentum of the rocket in kilograms meters per second? Use the equation momentum equals mass times by velocity. Right, we need to change 14 kilometers per second into meters per second. So that's 14 times 10 to the 3 meters per second, because it's 1,000 meters in a kilometre. Now we'll just multiply the two of them together to get the momentum. And that equals 7.7 times 10 to the 9. And we've multiplied kilograms by meters per second. So the answer is C. Part 2. The asteroid has a momentum of 7.5 times 10 to the 10 kilograms meters a second and a mass of 8 times 10 to the 6 kilograms. Calculate the speed of the asteroid. Right, so momentum equals mass times by velocity. Just like it's set up there. We need to rearrange that. So pop it in a magic triangle. M times by V goes on the bottom. P, momentum, goes on the top. We're looking for the speed, so cover up V. And you're left with P divided by M. P is the momentum, which was 7.5 times 10 to the 10. Divided by 8 times 10 to the 6 kilograms. And that comes out as 9375 meters per second. Just check the units are right. Those kilograms cancel out with those kilograms to leave meters per second. So that was correct. Part B, a 6 marker. A student investigates the effect of a crumple zone on the force exerted during a collision. The student has one trolley with a spring at the front and another trolley without the spring. With a spring, trolley without the spring. The student uses the arrangement in figure 13. After a trolley is released, it accelerates down a slope and bounces off a rigid wall. The speed of the trolley can be measured just before a collision with the wall and just after a collision with the wall. The silver foils are connected to a millisecond timer. The silver foils make contact with each other during the collision, so the time they are in contact can be read from the millisecond timer. The time they are in contact. Explain how the student could investigate the effect of a crumple zone on the average force exerted during the collision. Your explanation should include how to determine the force, right? You may wish to refer to an equation from the list of equations at the end of the paper. Yep, I know which one to use. How the effect of crumple zones may be shown in the investigation, and precautions that may be necessary to achieve accurate results. Right, the formula you want is impact force equals the change in momentum divided by the time taken for the change. Now what's going to happen is, as the trolley comes down here, if it's rigid, thump, it's going to stop very quickly, and that impact time is going to be small, which makes the impact force big. Whereas if you've got a crumple zone, that means that the impact time will be bigger. As the spring collapses, that foil will be in contact with this foil for longer. So if that time increases, then the force will decrease. If this time here is big, it makes the impact force smaller. Whereas this impact time is going to be very small, as it literally bounces off it, and it's not in contact for very long because it's so rigid. That means that the impact force is going to be big. So that is how the effect of the crumple zone will be shown. Right, I'll show you how to write that then. Right, first of all, to determine the force. If you haven't wrote that, you can write it as mv minus mu. So that is the final momentum, take away the initial momentum, divided by the time. Now we're going to need to measure the mass of the trolley. And we're going to need to measure the impact time. As I say to my students, base your explanation on the calculation and it'll make things easy. Right, how to get the effect of the crumple zones. So we need to do the experiment twice. Once with the trolley without the spring and then with the trolley with the spring. And we need to note the difference in the contact times. And as I said before, the trolley with the spring will have a greater contact time, so it'll have less impact force. And precautions or controls. Repeat the experiment for measuring the time and take an average. And other things you could do is make sure you start the trolley from the same starting position, have the same angle of slope, and release the trolley without pushing it. One, two, three, four, five, six, 7. So we've got our 6 marks there. Question C. Newton's third law, when applied to the collision of the rocket and the asteroid, as shown in figure 12, can be stated as follows. Right, why are they going back to the rocket and the asteroid after that last question? Anyway, the force exerted by the rocket on the asteroid is equal and opposite to the force exerted by the asteroid on the rocket. Explain how this statement links to the conservation of momentum in the collision. Right, it doesn't really matter what they're talking about. As soon as you see them say conservation of momentum, what that basically means is the total momentum before the collision is going to equal the total momentum after the collision. So that's where I always start. Now, if they're talking about the force exerted by the rocket on the asteroid is equal to the force exerted by the asteroid on the rocket, impact force we use the same equation we've just used on the crumple zone question about the trolleys. So the change in momentum of the rocket divided by the time, so the impact force in other words, will equal the change in momentum over time for the asteroid. However, the directions are different. Now, momentum is a vector quantity, and a vector has both size and direction. So we need to say that going to the right is positive, which means going to the left will be negative. So the change in momentum, the impact force, will be equal in size but opposite in direction, and that is represented by the sign positive or negative. So if we say the rocket going to the right is positive, that means we need to stick a negative sign in for the asteroid going to the left. Now the impact time is going to be the same if the rocket impacts for 0.1 seconds into the asteroid. That means the asteroid's impact time will also be 0.1 seconds because it's the same impact, so it's the same time. So therefore we can eliminate time from the equation, and that's what they've said. Explain how this statement links to the conservation of momentum in the collision. So the change in momentum of the rocket is equal in size but opposite in direction to the change in momentum of the asteroid. And we would get 1 mark for that and 1 mark for that, so there's your 4 marks there. Just in case it was worth 5 next time, you could say the conservation of momentum only works or only applies when there's no external forces acting. Conservation of momentum only applies when no external forces act. So that means the only forces we're looking at is the force of the rocket on the asteroid and the asteroid on the rocket. Anything else we'll have to ignore, and then it'll work out. Question 10. Figure 14 shows the hearing responses of a human, a mouse and a bird over a range of frequencies of sound. A part 1. Describe 2 differences between the hearing responses of the human and the mouse. Right, so the mouse is this dashy line and the human is the solid line. So the first thing is the human, a lot of stuff is happening at lower frequencies compared to the mouse's hearing. And if we look at the minimum intensity of sound detectable, the humans have got more sensitive hearing, because down here means it's quiet and up there means it's loud. So for a mouse to hear, the minimum intensity of sound is higher than the human. And generally, mice can hear higher frequencies than humans. So there's a few different things we could put. So mice can hear high frequency sounds better than humans. They're more sensitive to high frequency sounds. Humans are more sensitive to lower frequencies than mice. Now, to be honest, the examiners might consider those to be the same point, but like the opposite thing. So you might only get 1 mark for that. So we'll say that generally humans have a lower intensity of sound threshold, so they are able to hear. Minimum intensity of sounds is more detectable for humans. And another thing you could say is humans seem to have one low intensity, whereas mice seem to have two. Humans have one low minima, mice have two. That's the low minima there, and they're the low minimas. Part 2. A farmer wants to use an alarm to scare away these birds. State which frequency will be most effective and give the appropriate units. Right, when are birds most sensitive? It's when the frequency is, well, if that's 2 and that's 4, that'd be 3 there, so that's about 2.5 kilohertz. The volume of sound required for birds to hear 2.5 kilohertz is very low. So they only need the sound to be quiet and they can still hear it. If you try to use a sound that's about 7 kilohertz, the sound has to be very loud. So that's what this graph is showing you if you didn't quite understand from part A1. So that's 2.5 kilohertz and it's only worth 1 mark. So imagine if you did play 2.5 kilohertz loud, right, it's going to blast the bird's ears because they are very sensitive to that particular frequency. Part 3. State the reason for your choice of frequency in part 2. Well, that's what I've just said. The birds are the most sensitive to that frequency. They can hear it even if it's quiet. Part B. Describe the difference between infrasound and ultrasound. Right. Human audible hearing range. Humans can hear between 20 Hertz and 20,000 Hertz. Anything below 20 Hertz we call infrasound. Infrasound is sound lower than 20 Hertz, and ultrasound is any sound higher than what we can hear. So any sound higher than 20,000 Hertz. So 20 kilohertz. So ultrasound is above the threshold of human hearing, and infrasound is below the threshold of human hearing. Question C. A transducer can transmit and detect ultrasonic waves. Figure 15 shows ultrasonic waves transmitted by the transducer on the bottom of a ship. So there's the ship sailing along, transducer on the bottom, sending a signal out, getting the signal back to see how deep the sea floor is. The waves reflect off the sea floor and are received back at the transducer. The waves travel at 1,500 meters per second, so that's the speed. The time between transmission and reception is 48 milliseconds, so that's the time. I'd better convert that into seconds, so that's 48 times 10 to the minus 3 seconds, because milli is 1,000th. Calculate the depth of the water D shown in figure 15. So speed equals distance divided by time. We need d. Rearrange the formula to find d. So distance is on the top shelf here, so it goes on the top shelf there. Speed and time goes there. Cover it up, so d equals speed times by time. Now that distance though is going to be the distance there and back. So we will have to remember to half it to get the depth, which is just there. Put the numbers in. And the distance it's travelled in total, there and back, equals 72 metres. And we'll divide that by 2. That'll give us the depth. And that equals 36 metres. So if you're going to make a mistake, students tend to forget to divide it by 2. 72 metres is going there and back. So that's 36 metres and 36 metres. That's where your 72 metres came from. And the last question, question D. Explain how vibrations from earthquakes may be used to study the core of the Earth. Right, if we draw a picture of the Earth here, and what we've got is little seismic stations around the Earth. Now they basically detect earthquakes. They detect the seismic waves from earthquakes. Now just say you had an earthquake up here. Now there's two types of seismic waves. You've got an S wave. Now I like to turn the S on its side. If you turn it on the side, it's like that. Now what's that? That's a transverse wave. And the other type of wave you get's a P wave. And just remember, if the S wave's the transverse wave, then the P wave is longitudinal. Now longitudinal waves can travel through liquids. These transverse waves can't travel through liquids. Now your teacher should have told you about a thing called shadow zones. Now an S-wave shadow zone is all this area here. That means that all of these seismic stations, none of them receive an S-wave from the earthquake. Whereas the shadow zone for P waves is just here and here. Now, because of that, what we've discovered about the Earth, I mean, we know there's a crust that you walk on, but we've also discovered that inside the Earth is a core, and the core is actually made from an outer core and an inner core. And the outer core is actually liquid. So when the S waves travel down into the Earth, so imagine that was where the epicenter of the earthquake is, which means that's where it originates. The waves curve as they go deeper because the density is changing. And then when they get to that bit, they don't go any further. So you don't get any waves, any S waves getting picked up from the seismic stations there. And it does the same on the other side. So no waves, S waves get picked up there. So that must mean that this outer core is liquid, because we know that the S waves are transverse, so we know that transverse waves can't travel through liquid. Whereas P waves can travel through liquid. So P waves get picked up over here, just like the S wave. Now, why do they have just a little shadow zone here for the P waves? Right, well, when you get into the core, there is a sudden change of density So there's a sudden change of direction. And that sudden change of direction makes the wave not visible, not apparent. You can't pick it up on that section there. It comes down here, it's changing gradually because the density is changing gradually. But then here there's a sudden change of density. So wallop, there's a sudden change of direction. The same thing happens there. Boom. So you get this little section here where you've got a shadow zone. So any little stations, seismic stations here, don't pick up the P waves there. But they do pick them up here and go straight through and goes there. So these little stations here would be able to detect the P waves. It's just that bit and that bit where they can't. Now, how do we write that then? So we'll use seismometers or seismic stations to detect the seismic waves. So how can we use it to study the core of the Earth? So these seismic wave stations, the seismometers, will help us to detect different densities inside the Earth. S waves are transverse and P waves are longitudinal. S waves can't travel through liquid. Big S wave shadow zone shows that S waves can't travel through a part of the Earth which must be liquid. S wave shadow zone, which is big, shows part of the inside of the Earth must be liquid. The P wave shadow zone shows there must be different densities inside the core. So that point there is basically the same as this point here. Just this one's got a little bit more detail on. 1, 2, 3, 4, 5, 6. So if that was worth a 6 marker next time instead of just 4, I hope I've gave you enough information that you'll be able to get all 6 marks. Now well done if you've watched the entire video and you're learning. Your grades will definitely increase. That is an Obee guarantee. You're building what we call our System 2, which is slow thinking and methodical, but it helps to feed into System 1, which helps to recognise patterns quickly, eventually. So you are getting better the more you practice. That's a fact. Work hard, be nice, and I'll see you in the next video. Bye for now. Want to see more videos like this? Subscribe to my channel, GCSE Physics Explained.